All right, so in this video, we're going to talk about the ratio test. Again, it's another test to determine convergence or divergence. And it starts off by letting the series a sub n be any series. And then we're going to consider the limit as n goes into infinity of the absolute value of a sub n plus 1 over a sub n. And we're going to set that equal to rho. We're going to say the result of this limit is equal to the Greek letter rho. The results are, if rho is less than 1, then the original series converges absolutely, therefore converges. If rho is bigger than 1, then the initial series diverges. And if rho equals 1, then the result is inconclusive, and so we would need to figure out a different test to use to make our decision. So it's a very mechanical test. I'll go ahead and clear the screen and put up an example, but you'll see the mechanics of it are pretty convenient, and you'll pick up pretty quickly on when this test should be applied over maybe some of the other ones. Okay, so we'll take a look at this one, and I mentioned a moment ago that this test is perfect for certain types of series, and you'll see very quickly, because we have a factorial and because we have an exponential, this test is going to be pretty convenient. So I'll go ahead and get the limit set up. This is going to be the limit as n goes to positive infinity, and then in theory, remember guys, there's going to be this absolute value around here. Well, the absolute value is going to do away with the alternator. Okay, so if you look at these separately, these are both going to be positive. So with the absolute value bars there, this is what's going to go away. So I'm just going to focus on this guy right now, knowing that I've taken the absolute value of it. And we're to evaluate now at the n plus 1 here divided by the n, which would be this thing right here. So let me get this written out, and I'll go ahead and remind everybody where that came from. So that'll be an n plus 1 factorial over n plus 1 raised to the n plus 1 divided by the n factorial over n to the n. So if you remember the theorem a moment ago, this right here is the a sub n plus 1, and this would be the a sub n here on the bottom. Okay, so evaluate this guy at n plus 1, evaluate this guy at n, which is itself. All right, so now a little bit of algebra. We're still going to have here our limit as n goes to positive infinity, and then we have an n plus 1 factorial over n plus 1 raised to the n plus 1, then multiplied by the reciprocal of this. So n to the n over n factorial. All right. So now, let's clean this up a little bit more. Again, it's just going to be algebra, but it is pretty convenient how it works, which is why, again, the ratio test is nice in this case. So n plus 1 factorial is going to be an n plus 1 times n factorial. And in the denominator, this is going to be an n plus 1 to the n times n plus 1 to the first. And we still have this guy right here. Now, the reason why this was so convenient is because now the n plus 1 and n plus 1 can go away, as can the n factorial, leaving us with just the limit as n goes to positive infinity of n to the n over n plus 1 to the n. Okay? So now, this is one of these limits that we've seen before. We can manipulate it a little bit, and I think it's going to come out pretty nice. So just to be clear, we're going to have now an n over n plus 1 to the n, which is also going to be n plus 1 over n to the negative n, which is also going to be 1 plus 1 over n to the negative n. And so this guy right here is one of those limits that we've seen before. And you can certainly work it out using L'Hopital's rule if you'd like, but this guy ends up being 1 over e. The 1 over comes because of this negative. If that negative wasn't there, this whole thing would be just e, but because of the negative exponent, we're going to have 1 over e, and 1 over e being less than 1, therefore the original converges absolutely by the ratio test. So again, exponentials and factorials generally are a giveaway to use the ratio test. And by using the ratio test, what happened here is pretty common with what would happen in other problems. Now, this is an interesting one because of how this limit is one that we've seen in the past, and we were able to manipulate it and come up with it. But either way, once you get to this limit here or a limit here, use whatever techniques necessary to evaluate, and then, of course, make the comparison to 1, and then make your decision and draw your conclusion. All right, so now we'll take a look at what's called the root test. And much like the ratio test, it's going to be very obvious when to apply something like this. And conveniently, the approach, the conclusions from it are the exact same as from the ratio test. So we've got a series a sub n, and we're going to consider now the limit of the nth root of the absolute value of a sub n. We're going to say this limit equals rho. If rho is less than 1, absolutely convergent. Bigger than 1 diverges, and if rho equals 1, then the test was inconclusive and we would need to figure out a different approach. So all of these are the exact same as for the ratio test. So I'll go ahead and clear the screen, put up an example, and again show you why it's going to be pretty clear when you want to proceed with the root test. Okay, so we'll take a look at this one, and you can see we have this function here raised to the nth power. And we know that when we take an nth root of something, that can be rewritten with a rational exponent as 1 over n. So in this particular case, it's going to be pretty nice to use the root test. Now, it will start off with the absolute value as well. And so remember, if I put the absolute value bars in here, maybe I'll do it in a different color so it's easier to see. I put the absolute value bars in there before taking the nth root and then the limit. The only difference is going to be this negative. It goes away. The 2n is always positive. The n plus 1 is always positive from 2 to infinity. So the negative is the only thing that I'm going to ignore. So as I go ahead and write this out now, understanding what the absolute value bars are going to do, this is going to be a 2n over n plus 1 raised to the 5n. And then I need to take the nth root of that. So if I take the nth root of it, that's again going to put an n down here in our denominator. Okay, so remember the nth root is going to be a sub n to the 1 over n, which is what I did. Now, cleaning it up a little bit, we're going to have our 2n over n plus 1 now to the 5th. And so since that's now going to be raised to the 5th, this numerator is going to be 32 into the 5th, and the denominator is going to be an n plus 1 to the 5th, which if I were to expand that out, which I'm not, this would be an n to the 5th plus a bunch of other smaller stuff that doesn't matter. So it looks like the result of this limit is going to be 32. Since 32 is bigger than 1, we can say, therefore, the original diverges by the root test. So, much like the ratio test, when you're given an exponential or some factorials, it's easy to think that's going to work, and then it's very likely it will. Much is the case for the root test. When you have this power like you do here, that's normally a good sign to go ahead and move forward with the root test. If it's not going to work, again, it could come up inconclusive. We could figure out a different way. But for the most part, if I see something like this, that's kind of where my head takes me is let's try the root test first.